All right, I thought it'd be best to kind of look at independent and dependent in the context of the same problem. So you will want to have this in front of you. So again, your deck of cards, you have your face cards, there's 12. You have 4 suits, each of 13. You have 4 of each number, 4 eights, 4 sevens, 4 sixes. Half the deck's black, half the deck's red. So again, red is the diamonds and the hearts, and then spades and clubs are black. Okay, so we are going to be doing with replacement for part A. So with replacement, that is referring to independent. And without replacement, which is dependent. So again, when you're not putting everything back the way it was, it is going to have an effect on the overall probability. So for a face card and then the ace, so we're going to do part A, probability of face and an ace. And so we're drawing 2 cards. We're drawing 1 card, put it back, and then draw a second card, sorry. So the number of face cards in a deck is 12 over 52. The number of aces is 4 over 52. When you clean this up, you get 48 over 2704, which ends up giving you 0.0178. Now we do that same thing, but we don't replace it. So part B, still the same probability, face, card, and then an ace. So the first time won't be affected. It's never affected because nothing has happened. But now I'm going to hold on to this face card. So in my hand, I am holding this face card. So there is no longer 52 cards in the deck. There are 51 cards. And then the ace, just double check that the ace could not be a face card, and it can't. So there's still the 4 aces. So basically the only number that changed was in the denominator. So when you work this out, 48 over 2652, which is 0.0181. So you can see how little it affects the problem. All right, next we want a 2 and then a 10. So with replacement, probability of a 2, then a 10. So how many 2s are in the deck? There are 4 out of 52. How many 10s? Also 4 out of 52. You multiply that across, you get 16 over 2704, which as a decimal, 0.0059. Now we're going to hold on to the first card. So still probability of a 2 and a 10. So 4 out of 52 for the 2, but now there are not 52 cards in the deck because I'm holding on to that 2. And then can a 10 be a 2? It cannot, so it does not change the total of my 10s. I still have 4 10s. So 16 over 2652, which is 0.0060. All right, let's try with 3 now. So an ace, face card, and then a 7. So probability of an ace, then a face card. Whoops, that should say ace. And then a 7. So this time, 3 times I'm going to pull a card out. So first ace. So aces, 4 out of 52. And I'm replacing them. So you could go ahead and put these all over 52 because you're not holding on to anything. How many face cards? There are 12 face cards. How many 7s? There are 4 7s. Multiply everything straight across, 192 over 146.08, which will end up giving us 0.0014. Now when we do it, we're going to hold on to it. So probability of ace, and then face card, and then 7. Sorry, my writing is horrible today. So yeah, I'm going to pull 3 cards. So the ace will be exactly the same, but now I'm holding that ace in my hand. So now when I pick the second card, there's only 51 cards to choose from. The face card's not an ace, so I still am going to have my same number of face cards, which is 12. But now I'm holding these 2 cards, so now this goes down even further to 50. 7 is not a face card or an ace, so there are still just 4 7s. So the only time your top number can change is if you are pulling the same card multiple times, and it will make a little bit more sense when I show you this last example. Whoops, that's supposed to be a box. All right, so this last one, we want the probability of a king, then another king, and then another king. So as you can probably figure out, this is going to be almost impossible. Your number is going to be very, very small. So we want a king, and a king. So putting it back every single time. So 4 kings out of 52. We put it back. 4 out of 52. We put it back. 4 out of 52. So that's going to leave you with 64 over 140608, which is 0.0005. And now we're going to hold on to the cards when we're doing them. So probability of a king and another king. So just like before, we're going to hold on to that first king and it's in our hand. So when I go to pull the second king, there can only be 51 cards to choose from. But that first card is a king, so that's going to affect the number of kings because I'm holding one of the 4 kings. So for instance, if we look at our chart, I'm holding on to this king. It's in my hand. So now there's only 1, 2, 3 kings to choose from. And now I'm holding 2 kings in my hand, so there's only 2 kings to choose from out of 50 cards. So again, the only way for the top number to go down is if your first or second choices are the same as your third choice. And then multiplying this out, you get 24 over 132,600, which is 0.0002. So much smaller because we are taking away from the total data set.